Hey guys, welcome to the first week of e-learning. We're going to go ahead and go to Google Classroom and find the post that has the Unit 8 syllabus. And when we open it up, we're going to scroll down all the way past all of these topics that we did before spring break. And over here at the green, we're going to start with the first full week of e-learning starting on the week of March 23rd. Okay, there is a welcome back video. If you haven't already seen this, please do watch it. It's very, very informative about the layout of how we're going to actually carry out this platform online and go through the unit that is remaining and then the review for the AP exam and all that other stuff. It's very, very informative. Please make sure that you do watch this welcome back video. Then we do have a quick link that takes you to the informational outline of basically each week to week we'll have this posted on the calendars that we have on Google Classroom. Okay, so when I open this up, it will essentially give me the breakdown for what we're going to be working on this specific week. Okay, like we did change the due date to Tuesday, March 24th, 8:30 in the morning for the WebAssign Volume 2 assignment. It is for a daily grade. And basically just read through this. You could see that we are going to put videos on there. We're going to put blank notes and keys as far as the linked keys concerning Unit 8, Unit 8's syllabus. And then we're also going to look at the Delta Math assignment that we have that's due on March 29th. The Delta Math, that was a long AP review assignment where 50% is due by this date and 100% is due by this date. And we thank you, those of you students out there that already finished this 100%. You absolutely rock. So AP test, this is new information about the AP test. It is definitely reduced as far as what they're going to test, the concepts and topics that they're going to test. I'll let you read through this and click through that and kind of find out the changes. I would just mention the biggest changes are you don't have free response, or sorry, you don't have multiple choice questions on the test. It's only going to consist of, I believe, 3 15-minute free response questions, and that is it. Okay, so it's very conceptual, and it is basically just open-ended. Okay, so yeah, feel free to click on that link and find out more information about certain details. Just a reminder, our live tutorials that were available throughout the week are right here, and you can click on these links to take you to those tutorial rooms at these available times. And if you still need help outside of that, please give us an email. And then one more reminder, Padlet links you have for AB Calculus and BC Calculus that you can post questions from whatever we're doing. And we're starting like the week of March 23rd right here. Or if you had previous questions, just post it all here and we can answer them either here or even possibly record another video to answer certain questions. Okay, so please read the directions as far as how you're going to ask these questions, give them likes and so on and so forth, because those are the ones that are going to be recorded if they are in fact recorded. And then last but not least, looking ahead, we have a mini assignment or mini assessment that's going to be like a small little test for Unit 8. We know the AP exam will not consist of Unit 8 questions. However, through College Board, we're still encouraged to teach Unit 8 because you will need that stuff for college. Okay, so Mr. O'Brien and I are coming up with an assignment or an assessment in that regard. So please make sure that you do, in fact, learn all the material that is needed for Unit 8. Okay. And then you have blank copies and notes, the key, like I mentioned, and I'm going to record 3 videos. Okay, so I'm going to make them as brief yet thorough as possible because our goal is to make them as brief as possible, but at the same time, not rob you of any information that's going to just inundate us with questions either through the tutorial available times or on the Padlet. Okay, so we're still trying to be as thorough as needed in our notes and also on the videos. So the videos that I will be recording will consist of 8.1, 8.2, and 8.3 topics, okay? And they're in no particular order. It's kind of just all spiraled in and meshed in together, but they will cover those 3 topics for this week, okay? So let's go ahead and get started. Unit 8, Applications of Integration. All right, so we're going to review a couple of things that we've discussed in prior units, but at the same time extend further into deeper knowledge. For instance, displacement. We've heard the word displacement for a while now in calculus, and it is the change in position. So I'm going to go ahead and when I see the word displacement, I'm going to think change in position. Okay, change, which is that subtraction sign, in position. And from calculus, what we've learned is the change in position is equivalent to the area underneath the curve of a velocity graph. Okay, so this is first fundamental theorem of calculus, and we learned that f prime of x, the integral of f prime, is equal to, that is from a to b, the change in positions at two values, which is final position, f of b, minus the initial position, f of a. This is huge. This is the first fundamental theorem of calculus, okay? Area underneath the curve. Notice that there is a difference between the velocity function here and position functions there, okay? That is first fundamental theorem. All right, and just one more quick note is with this in mind, because it is displacement, displacement is allowed to be positive or negative. So areas below the x-axis are going to be negative, okay? All right, so now if I asked you to find the total distance traveled, that's something just a little bit different and an extension from displacement. So this is different from displacement in a slight detail where we're looking at only positive. So let me highlight that actually with red. Only positive areas is what we're going to interpret, okay? So positive areas meaning if you do in fact have something underneath the graph, it is not interpreted as being negative as it was up here with displacement. If you have negative graphs, okay, or negative areas, because of the fact that we're doing this absolute value piece, it's like everything is interpreted as being positive. So the positive areas, of course, are going to remain positive, okay? And this is just basic knowledge of absolute value. And the negative values, when we take the absolute value of those, are going to also be interpreted as positive. So everything, all the areas are positive. Okay, so that's the difference between displacement and total distance traveled. All right, let's move on. So displacement, if we arrange or rearrange this, we can basically move the S of A, otherwise known as the initial position, and we can move it over here to this side as far as to join in front of this velocity function, okay? So when I just move it over, I get this value right here. And then this S of B remains all by itself. And this is another way that we can see it. This is called the initial value equation. So the initial value problems that you will see in this unit revolve around this kind of rearrangement of the displacement equation, okay? And believe it or not, we've done this for a long time because this is kind of hidden as y equals mx plus b. If we think about algebra 1 topics, a y equals mx plus b is a linear line that starts at b, okay? And then it incurs some kind of change, and then its result is going to be a y position. Okay, and that's the same thing that is happening here. I'm going to start at a position. I'm going to incur some kind of change, okay? And this is called accumulated change. And then that will end us, this is also blue, and that will end up with us arriving at our final position. So our final position is going to be in red. Our initial position or our starting value is going to be in gray, and that's S of A. And then our accumulated change is going to be in blue. And we are used to seeing that with first fundamental theorem, the way I was showing you over here. We were used to seeing this as the accumulated change our final position, which is f of b, and then our initial position, which is f of a. All right, so let's keep going. It says a particle moves along the x-axis so that its time t is position. Its position is given by x of t. Now, when you guys have been looking at graphs or whatnot, you're used to seeing an x-axis and a y-axis, okay? But in this problem here, you're not going to have a y-axis because you're simply moving along the x-axis, okay? So it's like you're like a spring, if you will. You're either moving forward or you're moving backward. It's like you're moving forward and backward, but it's all just a horizontal piece that you're moving, like left and right, left and right, left and right. Okay, so visualize that. It's almost like spring questions like you do in physics and whatnot. Okay, another thing is you're used to seeing like x and y being like x is the x value of when and y is the y value of where, as far as like what is the position. You're used to seeing x, y like this, and this is like a point. This is your at value, and this is your actual value of that function. So at can be an interpretation of when. That's what we've been working with all year with calculus, which now we're going to call as t. And the value, the position, if you will, we're going to call x of t. So x of t is the position, and t is the time. So blue for t and then green for x of t. And the velocity is given by v of t. Okay, so match the following integrals with their verbal statements. Okay, so immediately by looking at these three equations, what pops out and gets my attention are these absolute value pieces. And they're inside of the integral. They're not like outside here. They're inside the integrand, and they're surrounding the velocity function. So already I should be thinking the total distance traveled. And yes, it is the total distance traveled from a low 2 to a high time of 7. Okay, so this is going to be C. Okay, looking at the other ones and kind of comparing and contrasting, I'm looking at this one that just looks like a displacement. Okay, and the displacement we know are these three key words: change in position. Okay, so this is going to be a displacement between a low value of 2 to a high value of 7, low to high, if you will. So this one is going to be B. And then finally, this one says, what is the position of the particle at 7? Okay, so if we want to know the position at 7, well, we know that 7 is going to either be one of these limits of integration, and since 2 is coming before 7 and it's lower, we're going to, by default, think it's from 2 to 7. Okay, and if I'm looking for a position, I should be thinking, and I'm given velocity, right here, this connection, I know that it's going to be the first fundamental theorem, which is from A to B, f prime of t, basically the displacement, is going to equal the change in position. Okay, so this is, again, I'm working with positions at 7, and I'm also given and correlating it with a velocity function. So I'm going to interpret first fundamental theorem of calculus, okay? So let me move that up here, and let's kind of like build around it as far as what goes where. So if I'm looking at this, I know that A, or low value, is 2. So that'll go here and here. And I know that my high value is 7. Oops, let me use a different color. That goes here and here. So I could essentially just replace this as 2 to 7 f prime of x dx is equal to f of 7 minus f of 2. And that's all from the first fundamental theorem of calculus. Okay? And this is saying, what is the position at, so let me highlight this in blue. What is the position at time is 7? That's the same as me highlighting this. What is that f of 7 when it's all by itself? Well, that means I'm going to move this f of 2 to the other side by adding it, okay, because it was subtracting over here. So when we move it to the other side, it's going to become a positive f of 2, and we're simply just going to add that accumulated change or that displacement of the integral or the area underneath the curve. Okay, well, let's go ahead and highlight up here. We know that f of 2 is the same as x of 2, which is right here. And then all this displacement that we're adding, basically the area underneath the curve or between the graph and the x-axis from 2 to 7 is going to be all here. And it will result with what we're looking for as far as the position. Let me highlight that in red, the position at 7. That's what it will end up giving our answer as. Okay, so this one's going to be A. So let's keep going. Now, we did it with an equation. Let's use the first fundamental theorem. And again, first fundamental theorem, just so I'm not copying it over and over again, is this one right here, which is what we started basically with displacement. It's first fundamental theorem, okay? We're now going to look at it with a graph. We did an equation, now let's use a graph. Okay, so we have a particle moves along the x-axis. Okay, so this is moving again along the x-axis, left and right. Don't think that it is this graph moving up and down. That's not the particle, okay? That's not the particle moving left and right. That is showing a velocity graph, okay? This graph right here is represented with v of t, okay? So if I were to label it, this would be v of t, and then my answer or my input variable would be t. That's what this graph is showing. But it says a particle moves along this x-axis, left and right, so that at time t, its position is given by x of t. Okay? X of t is a position that you don't necessarily see on this graph. It's just told to you correlated with x of t. So we can say at time 2, let me go ahead and write that down. At time 2, because again, we have a t, x of t, input, output going on here. So at time 2, the particle is located at 5. Okay, so that 2 is t and 5 is x of t. So let me write that over here. T is 2 and x of t is 5. So the following graph to your right shows the velocity function from 2, otherwise the low value of 2, all the way to the high value of 7. And we know from this equation here that the area underneath the curve is displacement, change in position. So I have two areas underneath the curve here. I have a positive area here from 2 to 5. And I also have a negative area here from 5 to 7. Okay, and positive area, you're going to think of throwing a ball upward or moving forward. Like you could say I'm driving forward in a car or walking forward. Or like if you're looking at something on a graph, it's like a spring, it's moving to the right. Moving to the right is this positive interpretation. But if you're looking at below the x-axis as negative, that means a spring or something that's moving along a horizontal line could be moving to the left. Or you could be dropping a ball that's falling from the sky. Or you could be in a car driving backwards. That would be negative displacement, okay? All right, so what we're going to do is we're going to look at our choices here of 3 plus 2. Oops. We have 3 minus 2, and then we have this value over here. Okay, so this 3 plus 2 and this 3 minus 2, these tend to be the easier ones. And I'm going to go ahead and this time gravitate to this 3 minus 2, which is a displacement. The reason why it's a displacement, it's a change between two positions. Okay, and the position for this first one is 3, And the position, or and the other position is 2. These are the change in positions. And the way that I want you to see this is the following. Let me show you that. Let me kind of slow down just a little bit with this displacement on part B. Let's go back to the graph, and we see 2 triangles. This triangle is 1/2 times the base of 3 times the height of 2, which is a positive 3. Where this triangle down here is 1/2 times the base of 2 times the height of 2, which gives us a negative 2. So this is a negative 2, and the reason why it's a negative is because it's below the x-axis. Okay, 1/2 times base times height gives me a negative 2 because it's below the x-axis, and up here was positive because it was above the x-axis. And if I were to basically start from 2, and go all the way to 7, I'm saying I could walk forward for 3 feet and then walk backward for 2 feet. That would be displacement, which means its accumulated change is a positive 1. Okay? Or I could have thrown a ball 3 feet up and then it fell 2 feet down. Or I could have been on a graph moving 3 units to the right, like up here, and then, so like 1, 2, 3 units to the right, and then 2 units back to the left. So my displacement ends up at a positive 1, which is right here. It's that positive 3, it's that negative 2, add them up together, that gets you the displacement or the change in position. So it would be B right here. Okay, let's go for total distance traveled. Well, total distance traveled, we know from previous slides that it's all positive. That's a positive 3 and a positive 2. So we know that it has to be A because it's total distance traveled. And that makes sense because this negative 2 over here, when I take the absolute value of the velocity function, it's essentially saying that there are no negatives. This triangle actually will kind of like vertically reflect, and it will pop up here so that the area is actually interpreted to be up here when you're doing total distance, which would be a positive 2. So traveling 3 forward and 2 back, its total is like saying like you're traveling 3 somewhere and 2 somewhere else. That gives you a total displacement, or sorry, a total distance traveled of 5. So that's why number 1 is A. And last but not least, over here with the position, we're looking at what is the particular position at 7. Okay, so I know I have a time of 2, I have a time of 7. I'm looking at a velocity graph that was given to me over here in this picture. So we're doing like v of t dt is equal to f of 7 minus f of 2. So when I'm looking for the position at 7, I'm looking for this. Okay, I already know that all of this is displacement. Okay, so let me highlight this in orange. All of this is displacement. It's the area underneath the curve that accounts for the positive and the negative combined together that got me a positive 1. Okay, so that displacement is here. And then finally, last but not least, to get my position of 7 all by itself, I'm going to end up moving this f of 2 over here like we did before, making it positive and adding it to this piece. And this negative, it goes away because you added to both sides. Okay, so it like zeroes out, if you will. So we have f of 2 plus this displacement. Okay, so f of 2 plus this displacement, f of 2 is representing what is the position at 2? Well, we know it's 5. Okay, let me highlight that so you can see it again. The position at 2 is 5. The change that was accumulated was all of this displacement. So it would be 5 plus 3 minus 2, which would give us 6. So the position at time t is equal to 7 is going to be 6. Okay, but nonetheless, this will be C. All right. And then this is another example similar to we did equation. we did graph, and now we're going to do table. Okay, so let's do this table right here. All right, so we have another moving along an x-axis. We're looking at a velocity function, but we're also looking at position. So velocity versus position. Again, I'm already thinking about my fundamental theorem. My first fundamental theorem of the integral of the velocity function is equal to the change in position. Okay, at time 2, my input is 2. Let me go ahead and put that as tx of t. That's my input output. My time is 2, so it'll be 2. My output, my position, if you will, my location or position is -1 at 2. And then we're trying to see what is the total distance, what is the position, and what is the change in position. Okay, so the change in position is going to have negative values as well. So that's the change in position, where again, the total distance traveled is all positive values. And then a certain position is going to be what is the displacement. Let me do that in red. This one over here was the displacement, aka the change in position. And what is that displacement added to an initial value or initial condition? Okay, or not initial condition, but initial value. Okay, so from first glance, from quick glance, it looks like the following. 1 is going to be B, 2 is going to be A, and 3 is going to be C. Okay, so just a quick review on this because it's been a while since we've done Riemann sums. We're going to use a left Riemann sum with the table that you see. Okay, and if you need to graph this, by all means do so. You can if you want. I don't think you need to, but let's say that we ended up graphing it and we said at 2 we were at -4. Then at 5, 3, 4, 5, we're at 6. 1, 2, 3, 4, 5, 6. And then at 7, 6, 7, we're at 3. So that we're looking at input, output. We're looking at input, output. And we're looking at input, output. This is our velocity function, if you will. And it's from 2 all the way to 7. Okay. Again, this is just the velocity function. So if I wanted to find the area underneath the curve, I'm going to have to look at certain interpretations as far as left Riemann sums, right Riemann sums, and midpoint, and so on and so forth. Okay. So looking at this, what I want to do is, we don't know if that's exactly what the graph looks like, but that's kind of like, I'm trying to get your brain wrapped around. When we go to Riemann sums, we're looking for rectangles. Okay, so let's go ahead and do the rectangles that are going to be built around these 3 points that were given here, here, and here. All right, so let's go to the first one. So it says using Riemann sums, so we're going to have 2. We're going to have 2 Riemann sums, basically a jump between 2 and 5, and then a jump between 5 and 7. So let's draw 2 rectangles. 1, 2, because we're going to have 2 base times heights. Okay, so let's go ahead and do the first one. This jump of x is 3. So the first one is going to be 3 because I went from 2 to 5. Okay, and yes, if I wanted to do that, I could do that over here as far as saying the jump was 3. Okay, the second jump is going to be from 5 all the way to 7, which is just a jump of 2. Which again, if I was looking over here, would just be from 5 to 7. Now comes a little bit of the tricky part. We're looking for a left Riemann sum. So that means the top left corner, or the top y value, is what this is going to come from. Well, this is a -4 because this is x and this is a y value. So we're going to put -4 here because this displacement becomes -12 because -4 times 3 is a -12. Okay, and then we're going to look at our second left endpoint, which is right here, and that comes from 6, because again, these come from the y values. These are the heights. So we have 6. And 6 times 2 is 12, so that's a positive 12. Okay? So looking at this, we can say that the change in position, which is displacement, is going to be a negative 12, because displacement can be negative, and it's adding the positive displacement basically above the x-axis, if you will, a positive 12. So that's why this checks out to be C. Where over here, what used to be a negative is now interpreted as a positive. And another positive, that's total distance, because everything is positive. And then last but not least, we have over here that certain position at 7. And again, that goes back to first fundamental theorem. Okay, and that first fundamental theorem I'm talking about is way up here. And we can build a from 2 to 7 of the velocity function, is equal to the position. So we'll say x of 7 minus x of 2. Okay, and we wanted to know the position at 7. So the position at 7, let me highlight that in gray, is talking about that position. So let's go ahead and move this by adding it to both sides. So that means this minus goes away. And that integral was already positive. And there is my x of 2, which is my position at x is equal to 2. So my position when x is 2 is negative 1. So all of this is negative 1. Okay, and then all of this remaining thing that was very, very similar to part C is displacement, which is all of that, because the displacement is the area underneath the curve, otherwise that integral of the velocity function. And that's how they connect. So now let's do a couple of problems. Actually, we're only going to look at these specific slides to find the total distance analytically without a calculator. We first want to partition our interval, and we want to look at zeros of f of t. In other words, look for all the x-intercepts of your velocity function, okay? All the x-intercepts, not just one. If there's 3, list them all out. Then we're going to integrate the velocity function between these zeros, okay? And then finally, we're going to just add the absolute values of each of the areas. So if the area was negative, we make it positive. If it was positive, it remains positive. And when we add them all up, we will get the total distance traveled. All right, so let's go ahead and look at this one. So we have a square of 1 by 1, that's a positive 1. We also have a triangle, which is 1/2, because it's 1/2 times base times height. And I'm going to say it's a positive because it's above the x-axis. Then we have a negative 1/2. And then we have, let's say, this huge rectangle of a negative 2, because base times height for that rectangle would give me a negative 2. Again, these are positive because they're above the x-axis. And these are negative because they are below the x-axis. Okay, so what we're going to do now is we're going to look at the displacement as far as analytically of how do we write this out as far as like change in positions or whatnot. So for this first one, all of this displacement we're going to say is a positive 1.5 or 1.5. Otherwise, what you're used to by now are improper fractions of a positive 3/2. Okay, and all of this negative displacement over here, because it's below the x-axis, is going to be a negative 3/2. So a negative, whoops, let me do that like this. It's a negative 3/2 because it's below. So again, displacement, it can be negative, which you clearly see here. And all you're going to do is add all the positives and negatives together. So if I add this negative 3/2, okay, it's the same as adding a negative is the same as subtraction. So it just becomes 3/2 minus 3/2, which you would have, actually, it's not 3/2. Let me do something real quick. let me highlight it in orange. This last part right here is a -1 because it was a bigger rectangle there. So it's like -1 is going to be added to this. Okay, so -3/2 minus 2/2. This is actually a -5/2. Okay, so -5/2, we're just going to add 1 to that. Let me just change it just real quick. This should have been -5. Okay, so that it would have been a -2 over a negative, oh, sorry, a -2 over a +2, which the displacement or change in position is -1. So kind of visualize this, maybe like you're standing still and you walk forward because it's above the x-axis 3/2 feet, so 1.5 feet. But then you walk backwards, okay, 2.5 feet. So what was your displacement? What was your final minus the initial? In other words, what over all that period of time was your change in from your original position? Well, you actually ended up 1 unit back than where you started. That's your change in your position. So throughout all the journey, if you will, moving forward and backward, your final change resulted in a -1. Okay. And then the total distance would have been and again, we're looking at all the zeros of the function and kind of separating them all out. This first 3/2 remains a positive, and this -5/2 becomes a +5/2 because we're interpreting everything as positive with total distance traveled. So then we would get 8/2, which is the same as 4. Okay, so up here you could say you changed by 1 foot. Okay, let's say that you traveled or your displacement was 1 foot backwards from where you originally started. But here, this would be 4 feet that you traveled, totaled. Like totaled altogether, you would have traveled 4 feet. That's the interpretation there. And the same thing goes with curves or graphs that are curves, not necessarily these rectangles and triangles. You identify all the x-intercepts, and this one's from 0 to 5. So we would basically look at this is negative displacement from whatever that area is. And of course, we would need the equation function of this blue function here. And then this is positive displacement. And if I'm looking at displacement, we could say that I'm going to approximate and kind of give these just values. Let's say that the top came out to a +10 and the bottom came out to like a -2. The displacement would be adding these together, okay, which gives me an 8. That means if I started wherever I started here, I accrued an 8 feet forward, if you will, is where I ended up. That is displacement. But if I said, hey, what was the total distance that you traveled from 0 all the way to 5 seconds, if you will, you would say I traveled a total of 12 feet because you're looking at everything. Again, this is where that absolute value comes into play. You're looking at each individual area as now a positive. So you would say 12 feet was the total distance traveled. All right. So that's all we have for the first video. The second and the third video